Hi, welcome to the final part of logistic regression video. In this section we're going to talk about goodness of fit and examining your model and outliers and things like that. One of the ways you can check an existing logistic regression model and tell whether it's any good or not is through the basic idea that if a model is good, data points and cases that have a high predicted probability of being an event probably are events, and cases that have low predicted probability of being an event probably are not events. They are non-events. And so this statistic called the Hosmer-Lemshow test is a good general way to check, do we have about the number of events that we would expect to from a good model. And what we do in this statistic is we break all of our cases, all of our data values into 10 groups. And these groups are formed evenly allocated groups according to the predicted probability from our logistic regression model. So the first group, the first 10% of our cases, have the smallest predicted risk or probability odds of the event, up to the very last 10th group, which are all the highest predicted probability events. And what we do for those cases is, for every one of the 10 groupings, we figure out how many observed events there are. OK is the number of observed events in the kth grouping, and EK is the expected number of events that are in that grouping. And the expected number of events are found by just adding up the predicted probabilities for each case. If a model is good, the observed cases, OK, will be roughly equal to EK, the expected cases, and this statistic will be adding up values that are quite small. The squared differences will be small between them. We're going to let this go from number of groupings 1 up to G, where G is usually about 10 groups. Sometimes if your predictor set is not very diverse and you only have a few category variables, you might not have 10 distinct groupings of different risk. And if that's the case, then you won't be able to use 10 groupings. You might only have to use 6 or 4 or something like that. Once you get down to 4 or 6 groupings, then you probably don't want to go lower than that, and this method wouldn't be appropriate. But if you've got 4 to 10 distinct groupings you can make, that would probably be good. This statistic has a null hypothesis that the model fits. The alternative hypothesis is that the model does not fit. And if this statistic gets too big according to a chi-square distribution with groupings, number of groupings G minus 2, if that statistic is too big, you reject the null hypothesis and you have evidence for the alternative. In R, we will invoke the Hosmer-Lemshow test using the resource selection package. This package requires that the response variable be coded as a 0 or a 1. So when you use this method, you might need to change a yes-no variable into a 1-0 variable in order to use the Hos-Lem test command, as I have done here. So what you do here is you have the predicted model response, and the second argument is the fitted or predicted values from the model, and you specify 10 groups, and these are the observed number of events. So in the lowest probability grouping, there are 4 observed events. In the highest probability grouping, there are a whopping 53 observed events and 3 non-events. What would we expect from our predicted model? Well, that's given down here in Hos-Lem test with the response, the fitteds, and the expected values. Here's how many events we were expecting. In the low probability group, we're expecting slightly over 5 events, and we observed 4. in the highest probability grouping, we observed 53 events, and we were expecting basically 53 events. So just a quick glance through this table looks like we're getting about what we would expect. Here's the basic command to get the statistic. Here's the x squared, or what we called C hat. This is the test statistic, 26.21. Remember, with 10 groupings, the degrees of freedom would be 10 minus 2, which is 8. And the p-value is very small, suggesting that there is significant lack of fit for these data. Here is another way to check the fit of a model. You've seen marginal model plots before, but you can do the same thing with logistic regression models. Here we have blue curves, which represent the pattern of event and non-event with respect to log diameter of our tree problem. And red is what is expected from the model. And you can see that the log diameter effect does not really match the data too well. It does okay, but not so good. It matches the severity effect really well, and overall sort of looks like it's a pretty good match for the data. And so this is a little bit in conflict with the Hosmer-Lemshow test, which says, oh, there's a problem with this model. But when we look at the marginal model plots, we don't really see any great evidence of really big problems. And so it's helpful to look at both kinds of methods to get an idea about what's going on. And one possibility is that for practical purposes, the model is maybe pretty good, but we have so much data that the Hosmer-Lemshow test is able to detect some slight problems. Our model's not perfect, but it's probably not horrible. Make sure you sort of calibrate your understanding of what Hosmer-Lemshow test does. When there's a lot of data, it will be very sensitive to small problems. When you look at the marginal model plots, we do see some small problems with diameter, but overall the linear predictor against the response is pretty good. Our model's not terrible. When we look at marginal model plots broken by species of tree, we can maybe understand a little bit about what's going on. It looks like the diameter effect is probably not as good for the black species, which is aspen. It looks like it's pretty good for the maples. And you can see overall it looks like both species of tree are not too bad. When we look at severity, we can see that aspens look like are behaving according to the severity effect pretty well. It looks like the red maples maybe are not having quite as good of a severity pattern matching the data as well. Another way to understand and know about problems and issues that might be going on with your data is through residuals. For logistic regression, it's a little bit more difficult because our response variable is either an event or a non-event. This y will either be a 1 or a 0. So a residual, if it's an event, will typically be 1 minus a predicted probability, which might be fairly large, and you'll get some kind of positive residual for events. For non-events, events that didn't happen, for cases, you'll typically get a negative residual, and Pearson residuals basically fall on kind of a -3 to +3 normal scale, because we're dividing by something that's roughly a standard deviation. So something might be an outlier if an event happened and y is equal to 1 for a case that we weren't expecting an event to happen. A real low probability case might kind of show up as an outlier. The other direction is possible too. You might have a non-event at 0 here for a case that you really were expecting something to happen, but it didn't. And that might be a way to get an unusual residual. So outliers can be expressed through residuals, and you can plot residuals against the log of diameter, against severity, against severity broken by species of tree. And what you're looking for in residual plots, again, are good residual plots basically follow a zero residual on average. And these aren't too bad, but you can see for aspens at low severity, our model's not really doing all that well. We're kind of notably drifting below a residual of 0. And in the middle severity of maple, we maybe don't do quite as well. We drift below 0. Residuals should try to hang around 0. Here's species with respect to diameter. And you can see that for small diameters, aspens have kind of funny behavior. And so maybe our model is not really fitting the diameter relationship quite as well, according to species. Here's the overall residuals plot against the basic linear predictor. This is probably the single most best residual plot that you can do. And you can see that our model kind of gets negative residuals and then sort of does positive residuals. And so this is not a perfect model, and we can understand why the Hosmer-Lemshow test flagged it as a problem. It's also not really horrible either, and you can see why our marginal model plots looked reasonably good. It's just sort of okay. And here's the basic residuals plot output from the ALR4 package. And you can see residuals plotted against diameter, species, severity, and overall. Not bad, but not that good. Little problems. You can see that with respect to diameter, there is some evidence of curvature. Remember, this is kind of a curvature test. So there is some evidence of lack of fit and curvature with that residuals plot according to diameter. You can measure influential cases in logistic regression, like Cook's distance. Remember, this might cases with abnormally large Cook's distance might signify cases that are overly changing your conclusions about effects, and you want to look at those carefully. Here's some plots you can do of Cook's distance against residuals. Here is a influence index plot, which you've seen previously, that has Cook's distances up in the top panel, residuals in the second panel, and leverages hat matrix values in the bottom panel. For this particular data set, we don't really see any Cook's distances that are very abnormal compared to any others. DF betas are another way to measure influence, and what you're looking for here is deleting a particular case, the jth case, how much, deleting case I, how much does it change the estimate of a predictor or a coefficient, beta j? DF beta's values are measured in standard errors, and so we usually think of things like half of a standard error or a whole standard error as being a substantial amount of influence or change. And you can plot DF betas and look for things that are like negative 0.5, negative 1, positive 1, positive 0.5. Those are substantial standard error changes in coefficients for deleting a single case. And for this particular model, we don't see any DF betas that are drifting up near 0.5 or 1. The biggest for diameter is about a 0.2. The biggest for the species is about a 0.3. For severity, we're not getting anywhere near a negative 0.5 or a positive 0.5. And for interaction, it looks like we get up to about 0.2 and negative 0.2. So these are fairly small standard error changes and don't suggest any problems with overly influential cases. The nice thing about DF betas as opposed to Cook's distance is Cook's distance just tells you whether you think you have overly influential cases. DF betas identifies what parts of your model will be affected. Model selection is also something you can do in logistic regression, just like you can in other kinds of regression models. In this overhead, I show what might happen to an AIC criterion if you drop one term from an existing model. And this would mean your AIC is 541.10 for this full model. If you get rid of the diameter term, notice AIC goes up, so signaling that you need the diameter. Getting rid of interaction also means the AIC goes up, so keeping the interaction is probably a good idea. This particular overhead talks about how to think about adding terms to a model. Here's a basic model called first mod, and maybe there needs to be more complicated structure than just a main effect for diameter, species, and severity. Maybe we need interactions. How do we know which interactions to do? Well, we could say, well, let's add interactions one at a time to first mod. This notation here means for all, tilde dot means all the predictors in the model, these, all the terms in the model. Think about level 2 or degree 2 terms of them. So in other words, interactions. And this lists what happens if you would add interaction pieces. You can see that the only one that drops the AIC statistic by adding it is the species by severity interaction. That looks like a good one to add. It drops the AIC statistic. You can also do a step function, starting with a model and going up to all interactions. And you can observe what happens here. It looks to either add or subtract terms. A plus means you're going to think about adding terms. A negative means getting rid of terms. And doing nothing at all to the existing model is right here. So the basic starting point is 543.96 on AIC. And the only step to make which will lower the AIC is adding the interaction. Here's another step command which specifies how complicated the model could be as an extreme and how simple the model could be. So we would go from the smallest possible model to be only severity, and the most complicated possible model is all the terms up to all interactions. And we finally get a result for what model we would want by minimizing AIC. Another thing we frequently do with logistic regression models is predict whether an individual might be expected to be an event or a non-event. And we do that through plugging in characteristics into our predicted model to get a predicted probability. As it says in here, you might have certain personal characteristics, and you might want your doctor to produce a probability that you would survive 5 years in this instance. How good is a model would be measured by how frequently high probability cases match low probability, high event cases. Do they match high probability cases? Do you get events for the high probability predictions? And we've seen that idea before in Hosmer-Lemshow. And another way to talk about that is the ability of a model to classify events and non-events correctly. And there are some terminology on this overhead that you should read and understand. The idea of sensitivity, what proportion of events get flagged as probably happening, what's the probability that an event will be flagged as an event if it's a true event, what's the probability that non-events will be correctly predicted to be non-events. Well, actually, let's see. Sensitivity is the probability that the subject tests positive that we think it'll have the event, given that it really did. The counterpoint to this is something called predictive value, and that would be for all the subjects that we think will have the event, what probability actually did. And all of the bullets on this page, we would like them to all be 1. A perfect classifying rule would correctly distinguish between and predict that non-events will really be non-events, events that we think should be events really are. And so the ideal thing is to have sensitivity and specificity and positive and negative predictive value all to be 1. And that usually can't happen. But you can evaluate your model in doing that, like with the code on this page, which uses some tools from the EPR package. What we're doing in the first part here is coming up with some predictions. And we're going to cut up our data set according to the predictive value of our model. And what we're specifying is that any predicted probabilities between 0 and 0.4 will be non-events, and predicted probabilities bigger than 40%, 0.4 up to 1, will be events. If we do that, how does our model do? Well, for all of the real events, there are 328 of them. 298 were predicted to be events. And so that, that would be the sensitivity. The positive predictive value would be something like, well, there are 388 cases that we think will be events, and it turned out that there were 298 of them. And that would be this positive predictive value. So the sensitivity is quite high, 91%. The specificity is pretty big, but not as good at 61%. The positive predictive value is 77%, and the negative predictive value is 82%. This model's pretty good at predicting actual non-events and actual events. It's not perfect. It would be perfect if there were 0 cases here where there were 30, and it would be perfect if there were 0 cases here where there are 90. That would mean that everybody that you think is going to have an event really would have the event. So that would be perfect. Notice we don't get it. On the next overhead, we changed the criteria to be a predicted event to be a half or bigger. And how do we do here? Well, we get a little bit better positive predictive value, and we get a little bit lower negative predictive value, and it sort of depends on the context about which kind of mistake you'd like to make. When you're diagnosing a life-threatening disease, you probably don't want to make a mistake and say that you don't have the disease when you really do. And so there are certain kinds of mistakes that are more crucial than others, and that might be how you decide where to make the event prediction cutoff. Another technique to help with logistic regression type situation where you have an event, non-event response variable is through tree building or classification trees. And the way this works is you need some new packages, the rpart or recursive partitioning package, and you specify a model just like you did for logistic regression. You have your event variable as a function of diameter, species, and severity. This output says that there are 559 cases, and the way you read this is at the beginning of the partitioning procedure, at the root node, there are 559 cases, and about 59% of them have the event. What we're trying to do is, on the next page you can see sort of a diagram. Here's this initial part right here, and what we need to do is figure out according to which predictors might most separate events from non-events. And it turns out that this algorithm went through and it figured out that the most distinguishing feature for all of these data points is severity. For severities below 39%, only about 33% of the trees died. And above that severity, notice the indentation, so we'd go to node 3, above 39%, notice that a very high fraction of the trees died. What you're trying to do in this procedure is split the groups of trees into as homogeneous a set of response values as possible. Ideally, you'd like to be able to make little groupings that are all dead trees or all alive trees. So we did a pretty good job separating alive and dead here. For the low severity trees, notice that the next most important criterion to split on is the diameter of the tree. And then after that, severity again. We eventually get to some species. For the high severity trees, notice the most important factor after that is the species. And variables that are important to understanding whether trees live or die are going to be the first breaks that are nearest to the top of the diagrams. The most important break of all is severity. The next important characteristics look like our species and then also diameter, but diameter looks like it's mostly important only for the low severities. When you get into the high severities, it looks like it's really just the species that matters. So this suggests maybe an improvement to our logistic regression model might be to have, say, a severity by diameter interaction. That might be something that would be suggested. It's really hard to read some of these splits later on. You can look back through the cascading diagram to understand what's happening. Notice that for split 4 and 5 on diameter, when there's an asterisk here, it means there's no further splitting. This node cannot find any additional predictor variables to help simplify whether trees live or die. If you can continue splitting and make progress, the algorithm will do it. As I said, it's sort of complicated to read this diagram, and so what you might want to do is trim it or prune the tree so that it's not quite so complicated and you can just understand the most important splits. And what you look for in the print CP function is you look for the X error, or the cross-classified error, to decrease and then increase again. And it looks like we hit a minimum in here somewhere. And so notice, because you're dropping the cross-classified error and then it's going up again in here. And so you try to find a place where that's fairly small. And I decided to cut it off at complexity 0.011, which is over here, the CP. So 0.011 is really right about here. So I'm going to cut the tree building at about this place where this gets to be a minimum. And you can see the tree again. It's less complicated and it's easier to visualize. You can see we split on severity. Over here we split on diameter. Over here we split on species, and then severity again, and then severity again. So severity is very important. Species is very important because it happens early on in the splitting. And then over here, diameter is important. So we need that too. And that'll help you make good logistic regression models. Sometimes even this classification tree is a good enough model to use just on its own. As always, let me know if you have questions.